All right, so for this next example, we're going to be looking at another graph, but in this case, we're not explicitly told what this graph is, whether it's f or f prime or f double prime. We're going to interpret it in a number of different ways based on the information given down here. So here's the graph we're going to be working with, but we're going to look at 5 questions regarding this graph. So the first one says, if the graph shown is that of f, so the original function f of x, find where f double prime is less than 0. So remember, f double prime is the second derivative, and we know that the second derivative of a function is less than 0 or negative anywhere that that function is concave down. So if this represents the original function, we're specifically looking for those intervals on which the function appears to be concave down. So starting over here, I can see that I have this downward curve, like downward opening curve, where we have concave downness. It's not really a word, but concave down, kind of in this general area over here. However, at some point along this part of the curve, it switches from being concave down to being concave up over here. And so that implies that we have a point of inflection around here somewhere. It can be a little tricky sometimes to identify exactly where that point of inflection occurs. So we sort of have to make our best guess. I'm going to assume that it's right here. And the reason for that is because oftentimes when we create graphs like this in a textbook, we want to use points and things that are a little bit more easily identifiable. I'm noticing that the curve passes through an intersection of these grid lines right here at the point -3, -8. And it does appear that there's this is at least very close to the boundary between when this curve goes from concave down to concave up. So my assumption here is that the example is wanting us to think that is the point of inflection. So for part A, I'm going to say that the first interval on which we have concave down part of our graph goes from here to here, which is -12 to -3. So I'm going to put that as one of my intervals, -12 to -3. Then we appear to be concave up all the way to here where we approach this vertical asymptote. And then after that, we appear to be concave down from where this vertical asymptote is. That's 2, that's 4, so 3 is right there. And then the rest of the graph goes off screen, but we're going to just assume that it continues this concave down trend all the way to infinity. So I'm just going to put infinity there. Okay, that's where this graph, oh, I just realized I was off screen that whole time. I have to remember to go back and forth. So again, looking up here from -12 to -3, and then from 3 to infinity, that's going to be the 2 intervals where we're going to say our function is concave down. Next up, part B. If the graph shown is still of f of x, find where f prime is increasing. You have to read these questions very, very carefully. It's not saying where f is increasing. I'm not looking for where this curve is increasing. It's not hard to find those places, but we're looking at the graph of f here, and we're specifically asked where a different function is increasing, not where this one is increasing. F prime, remember, is the derivative of f. And a derivative, or any function for that matter, is increasing if its derivative is positive. So this is the same thing as saying, when is f double prime positive? Okay, but we just answered a similar question. Up here, we looked at where f double prime is negative. So we're going to answer this one in a similar way, except now we're looking for the intervals on which this graph is concave up. So notice over here where we have a straight line, we don't have any concavity at all because it's not curved. And we identified 2 places where the function is concave down. From that point of inflection to that vertical asymptote, we appear to have a concave up portion of our graph, and that's the only concave up portion that I think I'm seeing here. So from -3 to +3, our function is concave up, and that's going to be the interval that we use to answer that question. Okay, part C, if the graph shown is of f prime now, so we're no longer thinking of this as f like we did for parts A and B. Now we're thinking that there is a function f, but what we're shown here is not the graph of f, it's the graph of its derivative. We're also going to assume that the original function f is continuous on its domain, and notice its domain here is represented as a union of 3 intervals. This is if you look at these 3 intervals and you think, what is in these intervals? It's the set of all real numbers except for -12 and except for 3. So we're going to assume that the original function is defined everywhere except for -12 and 3. And not only is it defined at all of those other real numbers, but it's continuous on all of those real numbers as well. We want to find where f double prime of x is greater than 0. You have to be careful here because, again, we normally would look at f double prime of x being greater than 0 as implying that we're looking for where a graph is concave up. But that's only if we're looking at the graph of f of x, which we are not in this case. We're looking at the graph of f prime. Okay, so f double prime is the first derivative of f prime. So to say that f double prime is greater than 0 is the same as saying that f prime is increasing. Okay, so now interpreting this graph as f prime, I want to determine where is this graph increasing. Okay, so we just look for that the way that we have before. It appears to be increasing from -12 all the way up to -7. -12 to -7. I'm off screen again, but I'm going to write these intervals down here. And then we are decreasing from -7 all the way down to what looks like 0 here. Then we are increasing from 0 towards this vertical asymptote 3. So we're increasing from 0 to 3. Again, I put that interval down there. And then we are increasing again once we get past that asymptote right here, all the way up until what appears to be this point at x equals 7. So I'm going to say from 3 to 7. Again, I wrote that down there. And then decreasing, from 7 to infinity. So all of the values after that, it looks like we're decreasing. Okay, so those are the 3 intervals I would cite there. And notice where we used the fact that the original function is continuous, not at x equals 3, because 3 is not in the domain, is when we split this interval into 2 parts. Even though this is the graph of f prime clearly doesn't exist at x equals 3 because there's a vertical asymptote, but sometimes that can happen and the original function f can still be defined at f equals 3. And in that case, I would have probably connected these 2 intervals and said that it's increasing from 0 to 7 in that case. But we have a split because the original function is not defined at 3. Let's take a look at part D. Part D says if the graph shown is of f prime, so we're again thinking of this as the graph of f prime, and if f is continuous on its domain, notice the first sentence is identical to this one. This time we want to find where the slopes of the graph of f are decreasing. Okay, so this one you have to read really, really carefully. So what does this mean? Well, we're not looking for where f is decreasing. We're looking for where the slopes of f are decreasing. The slopes of the graph, which literally means the slopes of the tangent lines to the graph. Remember, we get the slopes of a tangent line from f prime. So to say that the slopes of the graph are decreasing, then we're saying that f prime is decreasing. That's the literal interpretation of that. But if f prime is decreasing, that implies that its derivative is negative, its derivative being f double prime. So now we're looking for where f double prime is less than 0. But let's think about this for a second. We're shown the graph of f prime. I'm thinking of this as the graph of f prime, and so I want to find where its derivative. So I want to find where f double prime is negative. So I'm not looking at f double prime. I'm looking at the function whose derivative is f double prime. If we're looking for where f double prime is negative, then I'm looking for where this graph is decreasing. That's what I'm looking at. So we know that we're decreasing from -7 all the way down to 0. -7 to 0. And then it looks like after 0, I'm increasing again, and then from 7 to infinity, we appear to be decreasing yet again. Okay, last question. If the graph shown is f double prime, so this is the first time that we're going to think of this graph as f double prime. And again, if we assume f is continuous on the same domain that we've used in the past two parts, and f prime is continuous on its domain, so now not only is f continuous on this domain here, but f prime is also continuous on the same set of real numbers. What we want to do is find where f prime is decreasing. So remember now, we are talking about this thing being the graph of f double prime. And we're asked, where is f prime decreasing? Well, if f prime is decreasing, then the derivative of f prime, which is f double prime, must be negative. Okay, so I want to look for where f double prime is negative. But now this is the graph of f double prime. So I'm not looking for increasing or decreasing in this graph. I'm not looking for concave up or concave down. I'm literally looking for where this graph gives me negative values. That would be anything below the x-axis. So I have negative values from -12 to -10, because that's what's below the x-axis. -12 to -10. I'm going to include that interval. Then we're positive for a while, but then we're going to be negative again from -4 all the way to +2. -4 to 2. Okay, we're above the x-axis after that, so we don't use that. And then after we get past this asymptote, our function is negative from, this is x equals 3 to x equals 4 right there. So 3 to 4. We're positive for a little while, and then we go negative again once we get past 12. So that's 12, and it stays negative as far as we know through the rest of that interval, 12 to infinity. Okay? So depending on how we interpret this graph, whether it's f prime, or f double prime, we have to interpret these questions different ways. Okay? Now, up until this point, we haven't really dealt with any of the business or economics examples that we try to look at in this class. So what we want to do now is apply the ideas that we've been kind of going over to that kind of a context, to like a business example. Specifically, I want to look at how we interpret that point of inflection on a graph where we change concavity from concave up to concave down in the context of a business example. So think about this for a moment. If you're a company and you sell some kind of a product, obviously your goal is to increase profits, which means you want to increase sales in that in the process of doing that. That's how you earn profits. So to do that, to increase your sales as a company, you have to take some kind of an action to cause that to happen typically. And those actions require expenditures. You have to spend money to make money, as the saying goes. Oftentimes those expenditures come in the form of marketing and advertising. So the hope is that as you spend money on things like marketing and advertising, not only do you want the sales to increase, but you want the rate of sales to increase. You want to speed up the rate at which you are selling your product. Okay. Now, if you have a function f of x, and that represents the number of sales. Notice it's not a cost function or a profit function or a revenue function. It's literally the raw number of sales. And this time it's after X dollars are spent on marketing. So in most of the business examples that we've done, X has represented a number of units sold. We're interpreting X differently now. It's going to be interpreted as the amount of money you've put into marketing and advertising. It's a dollar amount. F gives us the total number of sales after spending X dollars. The rate of sales per dollar spent would be given by F prime, because again, we're looking at a rate of change in F. So if F represents sales for an amount of money spent, then F prime, the units of that would be sales per dollar. This rate is only going to be increasing when its derivative is positive. And remember, our goal is to make that rate of sales increase. So the derivative of F prime is F double prime. Our rate of sales will be increasing then whenever F double prime is positive. And that rate will be decreasing when F double prime is negative. So this is, I think the first time people take Calculus 1, or this calculus in particular, they have a hard time wrapping their minds around this. But a negative or a decreasing rate of sales does not mean that the sales themselves are decreasing. It means the rate at which you are selling your product is slowing down. So for example, if during week 1, if I'm selling at a rate of, say, 500 products or units per dollar sold, and then in week 2, I'm selling 300 products per dollar, or 300 units per dollar sold, I'm still selling products. My units or my sales are still increasing, but at a slower rate than they were the previous week. So that's what we would interpret as a negative or a decreasing rate of sales. So the point at which your rate of sales per dollar spent changes from increasing to decreasing, which again is the point at which F double prime switches from being positive to negative. We call that the point of diminishing returns, because what that essentially means is that you're putting a lot of money into trying to increase your sales, but the rate at which those sales are happening is now decreasing instead of increasing. So that oftentimes is the point at which you want to stop putting more money into marketing and advertising. It kind of represents a sweet spot, for example, of sort of an upper limit on how much money you can funnel into those things in order to continue increasing your sales. So point of diminishing returns. However, because that's a point at which concavity in f of x would be changing, because again, f double prime is switching from positive to negative, then that would also be the same as the point of inflection of the original function f of x. So a point of inflection on a function where that function is, as we defined it here, number of sales per dollar spent on things like marketing and advertising. The points of inflection on that graph represent points of diminishing returns. Specifically, the point of inflection where we go from a positive second derivative to a negative second derivative. It has to be going that direction. So let's take a look at an example now. It says big box store sells cardboard boxes in bulk to moving companies. The moving companies buy B of x equals this. This is our function. Thousands of boxes from big box store when it spends X $1,000 on advertising in a 2-month period. So notice the moving companies are buying from the big box store, which means these actually amount to sales for this company. Okay, so our function is a sales function, and the dollar amount, or the X in there, represents the dollar amount spent on things like our advertising. So this is the type of function that we talked about up here. We want to find the amount of money spent by big box at the point of diminishing returns, and then we want to round our answer to the nearest cent. So we need to locate that amount of diminishing returns. Remember, that comes from a point of inflection, which comes from the second derivative of this function. So the first thing we want to do is find the second derivative. What is b prime of x? Well, it's a polynomial. We've done these countless times now. So its derivative is negative 0.15 x squared plus 4.4 x plus 3.8. That's the first derivative. Again, using the power rule where necessary. Now I need a second derivative. X, or b double prime, is equal to, now I'm going to use my power rule again, negative 0.3x plus 4.4. Okay. So this here, excuse me, is the function that we got from our second derivative. My goal here is to find the point of diminishing returns. Now notice, if this is b prime, what we're looking at here is the graph of a line. This is a linear function. So it's got a negative slope and it's got a y-intercept, or really a b-intercept, or b double prime intercept if you want to call it that, of 4.4. It's going to be a line that looks like this, or at least that's part of it. Notice that as we pass through, or as we pass through 0 down here, we're going to go from being positive up there to negative down there. Our second derivative switches from being positive to negative. And this point right here would represent, whatever the x value of that point is, that would represent where the point of inflection occurs on the original function b of x. So because we're going to have a point of inflection at that x-intercept, and because we go from a positive to a negative second derivative, that will represent that point where we have diminishing returns. So to find that x-intercept, I want to set b double prime equal to 0 and solve that. Now this is very straightforward to solve. You would subtract 4.4 from both sides, divide by negative 0.3. So I'm going to get negative 4.4 over negative 0.3. And I'm going to actually do the division on that and get like an approximate answer. This one comes out to approximately, what is it? So like 11.9923, something like that. I'm actually going to double check my math here just to make sure I got that correct, because I did not do this one ahead of time. So, what did I say? 4.4 divided by 0.3. Oh, nope, that's actually incorrect. It's not that. It's going to be approximately 14.6667 approximately. Okay, so that's where the point of inflection is going to occur in this graph, and it's also where the point of diminishing returns will be. We're specifically looking for the amount of money spent, which is what this X value represents. But remember, X is measured in thousands of dollars in advertising during a 2-month period. So we want to find we want to multiply this by 1,000 to get the correct answer. So X would be equal to, if I multiply that by 1,000, I need actually another decimal there. It's going to be like that. 14,666.67. That's what that amount should be. Okay? I had the wrong number there originally. Okay. I'm going to end this video here. We're going to do one more and then wrap this section up.